Hi. In last class what we have seen? We have seen how we can measure the mechanical property of tissue. So, we were interested in measuring the elasticity of tissue, right, and for measuring the elasticity of tissue what kind of sensor we have designed? We have designed a piezoresistive micro cantilever. So, just to quickly recall, we have a tissue placed on a glass slide, and we have a cantilever that we are pressing on the tissue, and the cantilever bends depending on the elasticity of tissue, the cantilever will bend. Now, this cantilever is embedded with what? Piezoresistor. So, when it bends, there is a change in the resistance of the cantilever. This change in the resistance of the cantilever can be correspond or can be equate to the elasticity of the tissue. That is what we have seen, right. And if we can measure the mechanical property of tissue, then how about electrical property of tissue? So, when I talk about electrical property of tissue, what it can be? It can be a resistance, it can be a impedance. So, today's module is focused on how to design a sensor based on microtechnology to measure the electrical properties of tissue. Now, what are we getting by measuring the electrical property of tissue? Our goal is that as the cancer progresses, as disease progresses, will the electrical property of tissue change? And if we can correlate somehow using this sensor that as the disease progresses the tissue property changes, then that can be a marker apart from the existing gold standard, that is the biomarkers IHC, MRI, mammography. Now, we are adding one more modality based on the electrical property. Last time we have seen mechanical property. So, how can we design this sensor? How can we design this sensor? And it is again the heart of microtechnology is photolithography, right. So, let us see extremely easy way of designing this particular sensor using the photolithography and its application in measuring the electrical properties of tissue. So, if you come on the slide, we are interested in measuring the electrical property of breast tissue. So, this is the process flow. What we can see, if you see on the left side this particular chip, these are array of sensors and each sensor consists of an interdigitated electrodes inside SU8 well. So, if I place a tissue which is shown here onto this interdigitated electrode or interdigitated electrodes, can I measure impedance? Can I measure impedance of this tissue, right. So, let us see. So, if you concentrate on the this process flow, the first step is to take a glass substrate. Then we will use physical vapor deposition, either e-beam evaporation or thermal evaporation to deposit chrome gold, followed by patterning electrodes, So, how we can pattern this electrode, right, how we can pattern this electrodes. So, let us do like this. let me draw the process flow for you. So, it becomes easier, So, what we have seen, if you see, we will be concentrating on these two steps, from depositing chrome gold on glass to formation of patterned interdigitated electrodes. How can we do this? Okay. So, what we have? We have a glass substrate on which we have a thin layer of chrome and gold, chrome, glass. So, what will be the first step? First step would be to spin coat photoresist, Which kind of photoresist? Positive photoresist, So, let us draw photoresist in this particular format, this design, and we have our gold and we have chrome. So, glass, chrome, gold and positive photoresist. Next step, what is the next step? Next step would be to load the mask. What kind of mask? Bright field mask. Right now, it should be very easy for you guys to understand what kind of mask we will use, for which kind of pattern we have to use. If we are using positive photoresist, then which kind of mask we can use. If we are using negative photoresist, then which kind of mask we can use. Right? This can be now very easy for all of you to understand, since we have learned photolithography in detail in our earlier lectures. So, now on this I will load a bright field mask, right, a bright field mask. Field is bright, so it is bright field mask. What kind of photoresist we have? We have positive photoresist. So, what will happen? If I expose this wafer, then the area which are not exposed, by UV will become stronger. The area which are exposed will become weaker, right. This is your mask. This is positive photoresist, right, and this one would be your chrome gold. This is your glass. So, first step is, step 1 would be to spin coat positive photoresist. After that, step 2 would be to perform soft bake, right, spin coat. Second would be soft bake 90 degree centigrade 1 minute. Step 3 would be load the mask, and this is what kind of mask? Bright field mask. Step 4 would be UV exposure. So, step 4 would be, we will expose the wafer with UV light, right. Next step would be, step number 5 would be to unload the mask and photoresist developer. So, when you dip the wafer in photoresist developer, what you will get? When you dip the wafer in photoresist developer, you will get pattern which I am drawing right now. Correct? We will get this particular pattern. So, what will be my next step? Step number 6 would be hard bake, 120 degree centigrade, 1 minute, right. Next step, 7th. Next step would be to dip or etch gold followed by chrome, etch gold followed by chrome. How can we do that? We have to dip this wafer, in the gold etchant. After gold is etched, we can dip the same wafer in chrome etchant, and after you dip the wafer in gold etchant, you have to wash, you have to rinse it. So, after gold etchant, after etching gold etching, you have to rinse wafer in DI, okay, deionized water. Then you have to perform chrome etching followed by rinsing in DI. Okay. So, when you will do that, what you will achieve? You will get wafer with chrome gold protected where there was photoresist, and when where the photoresist was not there, the chrome and gold got etched, right. Chrome and gold got etched. So, this is your photoresist, this is your chrome gold, and this one is your glass. Next step would be step number 8 would be acetone dip. Acetone dip. Why to dip in acetone? To strip off the photoresist. To strip the photoresist, we have to dip the wafer in acetone. When we dip the wafer in acetone, what you will have? You will have this pattern. You will have a pattern of interdigitated electrodes. So, if you see here, what we got? A pattern of interdigitated electrodes from a glass coated with chrome gold, right. Now, what we said? That we said that these interdigitated electrodes should be inside SU8 well, right. So, for that, what are the process? So, now we know that, so I will just clear this one, right. We know that we have a wafer, a glass wafer with interdigitated electrodes, right. We have glass wafer with interdigitated electrodes, and what we want? We want that the interdigitated electrodes should be within a SU8 well, within a SU8 well. So, now we have to perform a photolithography in a way that we can create SU8 well, we can create a SU8 well, and when we look inside the well we can see the interdigitated electrodes. When we look inside the well we can see the interdigitated electrodes. So, let us start the process. The step 1 would be to take the wafer, glass wafer with interdigitated electrodes, right, chrome gold, chrome and gold. Next step would be to spin coat positive spin coat SU8 onto the wafer. Right, we had to spin coat SU8 onto the wafer having a pattern of interdigitated electrodes SU8. So, just let me draw the SU8 with some different design, which is your dotted design. All right. So, what we have done? This is we have taken wafer with chrome gold, glass wafer. Then as step 1 what we have done. So, this is step 1 of course. The step 2 would be to spin coat SU8 onto the wafer, right. Next step. So, what is SU8? SU8 is a negative photoresist. SU8 is a negative photoresist. All right. So, after you spin coat SU8, the next step would be, step number 3 would be soft bake. Now, in case of SU8, the soft bake temperature is around 65 degree centigrade. Depending on the thickness of SU8, the time for soft bake would be different. After soft bake, we have to load this SU8, load the wafer spin coated and soft bake with SU8, soft and spin coated with SU8 and soft baked with a mask. So, what kind of mask we will use? We will use a mask. So, let me draw it little bit in the center of the screen, so that we understand clearly. This is very important process, Okay. So, what we are talking? We are talking that we have interdigitated electrodes covered by SU8, and then on that we are loading a mask. SU8 is a negative photoresist. So, now SU8 chrome gold and this is a mask. So, in case of negative photoresist, what will happen? The area which is not exposed, will become weaker. The area which is exposed will become stronger, right. What we want? We want well. So, what we will do? What kind of mask we should design? We should design a mask in this particular fashion. So, stay with me. The area which is not exposed will become weaker. So, if I draw a mask, in this particular fashion, and perform UV lithography. Why we want to do this? You see here, what I want to remove from here, I want to remove from this area, right. So, if I draw this kind of mask, right, if I use this kind of mask and perform UV photolithography, what will happen? The area which is not exposed by SU8 will become weaker, right, and the area which is exposed will become stronger, correct. So, after UV exposure, what we have to do? Next step would be this will be fourth step, and UV exposure would be fifth step, right. UV exposure would be fifth step, loading mask would be fourth step. Okay. After this, sixth step would be hard bake. It is little bit trickier compared to negative photoresist SU8. After soft bake and UV exposure, you have to perform hard bake before you go for developing the SU8 material. So, hard bake is done around 90 to 95 degrees centigrade for x amount of time depending on the thickness of SU8. Okay. So, that is the next step, right. After hard bake, you have to develop SU8. When you develop SU8, what will get? You will get a wafer which looks like this. Sorry about that. Okay, and this would be correct. So, SU8 and this one is our interdigitated electrodes with chrome gold, right. So, this one would be my SU8, this one would be my interdigitated electrodes, right, and this is my glass, right. So, when I perform this experiment, what will I get? I will get a patterned SU8 well. I get a patterned SU8 well, right. So, from glass to an interdigital electrodes within SU8 well, we have seen the process. So, how it will look like? It will look like the one shown in this particular figure. What is this figure all about? There are interdigitated electrodes which are of chrome gold, and these interdigitated electrodes are within SU8 well. There is some difference between this figure number 1 and figure number 2. What is the difference? You see closely, the spacing between the interdigitated electrodes is about 10 microns. The spacing between interdigitated electrodes in figure number 2 is 30 microns. The width of the interdigitated electrode, each electrode, the width is 10 micron. So, 10 micron width, 10 micron spacing, 10 micron width, 30 micron spacing. Okay. So, this is how we can fabricate an interdigitated electrode in an SU812. You can also say that this is a biochip, this is a biochip. Now, on these interdigitated electrodes we will place tissue. So, if you see this particular figure, what you see here is we have placed a breast tissue core onto the interdigitated electrodes, right, and the thickness of breast tissue core is close to 4 microns, 3.83 to 4 microns. This is a cross sectional image of the breast tissue core, this one SEM image, cross sectional image of the breast tissue core. You can see here the interdigitated electrodes at 20x magnification, this is at 4x magnification, interdigitated electrodes inside SU812 on which the breast tissue core is placed. So, what we will do now? Once we place the breast tissue core, to keep the breast tissue core in a intact position, we have to load something called PBS, phosphobuffer alright, so that the tissue is preserved, so that the tissue is preserved. So, now if I load this PBS onto the tissue, then it should look like this, right, that I have the contact which is for measuring the impedance, I have a tissue slice which is my breast tissue slice, and then I have PBS solution to preserve the tissue. So, now if you closely see what we find that the electrodes from here to here forms a double layer capacitance, from here to here again forms a double layer capacitance. This tissue and PBS solution will form the resistance and capacitance which will be your ZT. There will be resistance of the PBS solution which is your RPBS. So, schematic of the bioimpedance measurement issue and equivalent circuit you can see from this particular figure, right. So, what we are measuring now? We are interested in measuring the impedance of the tissue which is your net impedance, So, how to measure that? We will use an impedance analyzer. And we have tried two different kind of tissue. One is benign and another one is cancer. Benign and cancer. And we have measured impedance as well as the phase, impedance and phase. So, what we found? We found that around 200 kilohertz, we were able to delineate the cancerous tissues from the benign tissues, the cancerous tissues from the breast or breast cancer tissues from the benign tissues. So, now this method of using the interdigitated electrodes within the SU812 can be used to delineate between benign and cancerous tissues, right, if we have the impedance analyzer. And we have considered several cases which you can see in this particular figure. And which kind of electrodes we have used? We have used the electrodes which are 10 microns in spacing and 10 microns in width, because the 10 microns in spacing and 10 micron width electrode would cover a better cover a larger area of the tissue compared to a 30 micron wide electrode. So, sensitivity will be different, if not at all. In a simple terms, the sensitivity of the electrodes which is this electrode number 1 would be higher compared to the sensitivity of the electrodes which are 30 microns spaced and 10 microns in width. So, the results that we can see here are obtained using 10 micron width electrode with 10 micron spacing. Same thing if you can see for the phase angle, you can clearly see that we can delineate the benign tissues from cancerous tissues based on phase as well. Now, one thing to measure here or to understand here is that if you see these cases, right, these cases are much more closer to cancer tissues. What could be possible reason? What could be possible reason? The reason was that these tissues were older, these tissues were way older. So, how we got this tissue? We got this tissue from tissue bank. So, in the tissue bank they preserve the tissue. So, these tissues were older compared to these tissues were comparatively fresher, newer, and with time also you see the change in the property of the tissue. So, our idea is not to wait and get the tissue from the tissue bank, but to understand the properties of tissue from the biopsy, from the immediately after biopsy. Immediately as soon as the tissue is taken out, we should have some kind of technology that can measure the electrical, mechanical and thermal property of tissue and get the understanding between the normal tissues, benign tissues, invasive ductal carcinoma, lobular carcinoma and as well as in situ, lobular carcinoma in situ, right, ductal carcinoma in situ, invasive lobular carcinoma, invasive ductal carcinoma, benign, normal. This delineation can be made and we can aid the clinician, we can aid the pathologist using this tool that we are planning to develop. For understanding the electrical, mechanical and thermal property of tissue, first thing is to understand the mechanical property of tissue that we can measure with the help of cantilever. Now, we in this lecture or in this module, what we have seen? Electrical property of tissue. So, how can we integrate electrical and mechanical both sensors onto one chip? And if we can measure electrical and mechanical, what about thermal property? Can we integrate all three things together, electrical, mechanical and thermal properties, and have a biochip on which we can load the tissue and get the measurements and get the delineation along with the existing technologies? We are not replacing any technology. What we want is we can aid the pathologist to reduce the false positive and false negative signals, right. So, what we understand from here is now we can measure the mechanical property of tissue, now we can measure the electrical property of tissue. So, in the next module we can design a sensor that can perform both electrical and mechanical property of tissue, right. So, I will see you in the next class. Till then you just go through this particular module once again, understand it, how you can fabricate a simple sensor to measure the electrical property of tissue. Now, when I talk about tissue, it is not just limited to tissue, it can be used for understanding the properties of cell. So, if you load the cell and measure the property of cell, you can again delineate between normal cells and cancerous cells, right. So, I will see you in the next class. Till then you take care and read this thing once again, so that when we understand the next sensor in the next module, you can correlate the understanding of this particular module with the next one. I will see you in the next class. Bye.